kind introduction. I'd like to be able to say that MIT stands for the Minnesota Institute of Technology, but it's the other one that I went to, sadly. So it's a real pleasure to be here tonight.
Can you turn that down a bit, Peter?
Long delay of
Softer.
COVID notwithstanding, to share with you this voyage that a number of us have been on over the past decade and more, to try to take a photograph of a black hole. It seems impossible, but
One more.
that's a lot of what scientists do. We dream of what could be, and then we set about to making it so. And we thought that if we could take this image, if we could make an image of a black hole, we'd be able to test Einstein's theory in one of the only places in the universe where we know it has to break down, or where it could break down. And we'd also be able to study all the physical processes that occur close to the black hole, because we know that black holes are ferociously efficient engines that change the way the night sky looks. And I'll show you some examples of those. So the idea here is we're going to lay a ruler across space-time, measure this feature that was predicted by Einstein 100 years ago, and we're going to say something about why the universe looks the way it does. So it starts with this guy, who's this mustachioed fellow, as we call him, who needs no introduction. And he came with this new idea of what gravity was. It was not a mysterious force between two objects, but it was a deformation of space-time. So matter deforms space-time, and then that deformed space-time in turn tells matter how to move around it. Okay, so this was a new way of thinking about gravity, and right away, it changed how we understood the orbit of Mercury. So for many, many years, the orbit of Mercury had been a mystery to astronomers. For some reason, it would precess. It wasn't always on the same orbit. It moved slightly every year. And they came up with a lot of mysterious reasons for why that might be, but ultimately the explanation was when Mercury gets close enough to the sun, these new gravitational effects take hold and they change the orbit of the planet. And then the real clincher was during a total solar eclipse. Einstein predicted how much starlight would be bent around the limb of the sun. So this is the actual star's position, but we would see it slightly offset because of the light bending due to the sun's force of gravity. And this is only, we call it 1.7 arc seconds. That's astronomers speak for 1/2000th of a degree. So they needed to use the best astronomical instrumentation of the time just to detect this. And that's a theme of the talk tonight, using the best instrumentation to make the most precise measurements to test fundamental theories. And this is what they found. So Sir Arthur Eddington mounted two expeditions, one to Sobral off the coast of Brazil, and one to Principe off the coast of Africa. And this is an image taken from Principe, and you can see during this total solar eclipse, the corona of the sun is clearly visible, and these horizontal bars mark the positions seen of these stars, and they matched Einstein's predictions and not those of Newton. So in one fell swoop, Einstein became a household name, and I love this title, Lights All Askew in the Heavens. Men of science, more or less, agog over the results of eclipse observations. Like, I aspire to have someone write about my research and use the word agog. But I think those days are past. Also something about the Kaiser, but that's for a different talk. But this is one of those moments where our entire thinking about the universe changed. Okay, but the implications of this theory were yet to come. It took many years for us to fully digest what these meant. Now, one of the things that didn't have to wait was this idea of a black hole, although it wasn't known as a black hole at the time. So Einstein came with his theory in 1915, and just 1 year later, Karl Schwarzschild, again with the mustache, was on the front in World War I, and he solved Einstein's equations. Einstein did not think this would be possible for many years, but he found a very key single solution. What if all the matter was in a point? What would the gravitational field around that point look like? And what he realized was you would get a deep, deep gravitational well. Things would fall towards this point. And there was this membrane, this imaginary point called the event horizon. And once you approached the point mass and you went through that event horizon, you were never coming back. Okay, because no force could resist gravity at that point. So it was a point of no return. And the Schwarzschild radius for those of you who like some of the numbers, is just 2 times Newton's gravitational constant times the mass of the object divided by the speed of light squared. There's a handful of constants telling you how big, how close you can get to a black hole before you're sucked in forever. Now, for a long time, people didn't think these would be possible to see. They didn't even think they existed. But things started to get a little strange, and it wasn't just the normal matter that makes up this desk. It wasn't the air around us that governs the way things exist in other parts of the universe. We began to see things like white dwarfs. Okay, these are stars that have blown off their outer layers. They're about this mass of our sun, but they're the size of the Earth. So extremely dense material, 1,000,000 grams per cubic centimeter. 1 teaspoon would weigh about a ton. So people could see these objects in the sky, and they began to realize it's not a black hole, but it's getting very, very strange. And then a neutron star is the next step. So when you get a much bigger star, it can collapse even more until the substance is only neutrons. And that neutronium, as we call it, is extremely stiff material. It's so dense that 1 teaspoon weighs 100 million tons. And the density is really best described by astronomical notation here, exponential notation. This is the mass of our sun, but the size of Minneapolis. Still, this is not a black hole. You could, in theory, escape from a neutron star. A black hole happens when you get enough mass, a big enough star, and at the end of its life, the internal nuclear fuel is insufficient to resist the force of gravity, and it collapses into what we think is a singularity, a point of infinite density. Okay? And we've seen these types of black holes because the Laser Interferometry Gravitational Wave Observatory has seen them or heard them merge. And we've heard the ringing of space-time when 2 black holes come together. There's very good evidence that these now exist at this level. Now, what got me into this field was a picture like this. Okay, so here you see a galaxy, Hercules A, about 4 billion light years away. And at the center, there's almost certainly a black hole that weighs 2 billion solar masses. And we know that because, well, this is what it looks like in the optical, this is what it looks like in the radio. Okay, so if you put radio goggles on, you see something entirely different. Okay, and what you're seeing here are jets of material being released, and they're flying out at roughly the speed of light, close to it. And they go for 1.5 million light years. They pierce the entire galaxy. They're much larger than the galaxy itself. The only thing we know of that can be powering that is a rotating supermassive black hole that weighs billions of times what our sun does. And magnetic fields are caught in that black hole, and they rotate. And like beads on a wire, charged particles are flung out because they're constrained to move along those magnetic field lines like an egg beater. And you wind up with these diametrically opposed jets that can stream for millions of light years. Okay, so we reasoned that if we could image this, if we could zoom in on this picture by about a factor of 1,000,000, we'd be able to test Einstein's theory and also see what powers these jets. Now, how do these, maybe that's Einstein. Maybe that's like, he wants his picture back. Or, so one thing to ask is, well, why do black holes shine? I mean, if they're defined by this ability to devour light and light can't escape, then why are they some of the brightest objects in the universe? And one of the ways I like to explain this is by showing this apple. If I were to drop an apple on the stage, it would release about a joule of energy. A joule is just a unit of energy. That's enough to power your cell phone for about a second. The key of a black hole is that even though it might weigh the same as the Earth, so if you scrunch the Earth into the size of a marble, okay, far enough away, you couldn't tell the difference gravitationally because the gravitational field far away would be the same. But if you drop that apple the same distance, the radius of the Earth, when it finally approached the interior of the black hole, it would be traveling very close to the speed of light, and it would release 10 to the 16 joules. Now, how big a number is that? That's enough to power all of Manhattan for a full year. So same apple, same mass, but just a different condensation. And you wind up releasing a huge amounts of energy. And this is what happens with black holes. They accrete mass to them. It has to get into an impossibly small region. It heats up because all this mass is rubbing up against each other, and it heats up to 100 billion degrees, and it glows brighter than any star. So now we ask ourselves, well, how big would a black hole look if we could actually see one? What would it look like? And we can go back over 100 years to Max von Laue, who said, well, the way I can figure this out is by sending light rays back to the black hole, and I'll see which ones are absorbed in the event horizon and which ones escape, and that will tell me how big the image of a black hole can be. So here's the event horizon, and we know that's the cause of the shadow that we're going to see, the shadow cast by the black hole against the hot gas that surrounds it. But it's really this point here, the circular orbit around the black hole. This is where light just isn't sucked in, but it moves around in a circle. That defines the size of the shadow, because when you fire a photon or particle of light back in, this is the trajectory where it just starts to orbit the black hole. Everything interior to here will be caught by the black hole, so it'll be dark. And only outside of this region will we see something that's bright. Okay? Now, this is what you think a black hole might look like if you've seen the movie Interstellar. Okay, and you can see here that photon orbit, the thin ring here, and the size of that shadow is shown here. The reason that you're seeing a top and a bottom here is because the orientation of a accretion disk, the orientation of the disk that's feeding the black hole, winds up being lensed above and below. So you wind up seeing what's behind the black hole. Pro tip, never try to hide behind a black hole, right? There's nowhere to hide behind it. And we know this is the case because in 1979, Jean-Pierre Luminegue, this visionary French astronomer, simulated this. So think about this. 1979, they were simulating what a black hole would look like. And he said if you had an accretion flow around it, you get some light that comes down below the black hole and lens up. Some that comes up, you have a direct image, an indirect image, and you wind up seeing this telltale shadow. Now, Jean-Pierre, being a little bit of an artist, took his computer simulations and hand painted in India ink on negative paper dots that replicated all of these simulations, and you can see that here. And then, not being content with that, as far as I know, he made the first simulated movie of a black hole, showing what you would see if you were at the black hole with a disk orbiting the black hole. Now, the hot gas is orbiting, is all around the black hole, and this animation shows that that hot gas, which represents photons coming from all directions, puts on our screen, or the image that we would see here on the Earth, a ring with a lot of tufty material around it. And it's the size of this ring, which is, when you go through Einstein's equations, as I know we all have, right? So when you go through that equation, you wind up with the square root of 27 times the Schwarzschild radius, whose formula I gave you before. This is pretty interesting. So when I saw this, I thought this is something that we should really do. Because if we could measure this with any technique, laying a ruler across that feature, we'd be able to measure the mass of the black hole, knowing its distance, and test to see if Einstein's theory held at the black hole boundary. And there's been a whole cottage industry of people doing tremendous work on high-performance computers, showing what this might look like. So, early work by Heino Falk and his collaborators, Avery Broderick, Charles Gammie and his group. And in all of these, you wind up seeing that one side is brighter than the other side. And that's because the gas moving around the black hole is going so quickly, near the speed of light, that when it comes towards you, it's Doppler boosted, and so it's brighter, much the way the train whistle is higher in pitch when it's coming to you. And on the other side, it's dimmer because it's Doppler deboosted, much the same way that a train whistle is deeper in tone when it's moving away from you. And we've even made movies of what these things might look like if we would capture them in real time. Now, the best case that we know of to try to look for this is in the center of our galaxy. So here you see the Milky Way in optical light. And if you zoom in to the very center and you look in radio waves, you'll see streamers of material all moving through the center of our galaxy. And that white dot here is almost certainly the position of a 4 million solar mass black hole. So our own galaxy has this supermassive black hole at its center. And we know that to almost a certainty now because of the great work by Andrea Ghez and Reinhard Genzel, who won the Nobel Prize in 2020. And you see here the positions of stars around the black hole. These are stars making orbits around an unseen mass. This is the only place where you'll see stars being tossed around like they were planets. And as I like to say, if this doesn't knock your socks off, your socks are on too tight. Okay, because this is really a unique place in the entire universe. Okay, and this is what gave us confidence that we were looking at a supermassive black hole there. Now I'm going to tell you about how we made this image. We had to overcome a number of different problems. And the first problem is that if this is a simulation of the black hole at the center of our galaxy, it depends on which wavelength of light you observe it at. So this shows you what it would look like at a wavelength of 3.5 millimeters, or about 90 gigahertz, okay, the same kind of radiation that your cell phone would use. But between us and the galactic center, between us and the center of the Milky Way galaxy, there's a scattering screen. Okay, there's gas that causes the radio image to be fuzzy. So it looks like this. So you can't observe it at this wavelength because you're only going to see a big mess. At a wavelength of 1.3 millimeter, because the scattering is frequency dependent, the higher frequency you go, the shorter wavelength, the less severe the scattering is. So you can start to see that circular feature. And when you get all the way up to 0.8 millimeters or 350 gigahertz, then you can start to see things. So we knew that we couldn't observe at this long wavelength. We had to observe something like 1 millimeter in order to be able to see this feature. That's the first thing. The second hurdle was all that hot gas that's surrounding the black hole shields it. We needed to be able to see through the very hot gas that was surrounding the event horizon. So M87 is the next kind of object that we can look at. It's also a supermassive black hole. It weighs 6.5 billion times what our sun does. It's 55 million light years away. And it is ejecting those jets that I showed you before. You see one jet coming towards us, so it's Doppler boosted, we can see it. There's another jet going almost directly into the page. So it's Doppler deboosted and it's invisible to us. Okay, if you zoom in by a factor of about 100,000, you see this jet getting closer and closer to the black hole, but you can't see the black hole itself. Only when you zoom in by about a factor of 1,000,000 can you start to see what's just around the black hole. But the other reason to go to shorter wavelengths is this. When you start at longer wavelengths, it's opaque. And only when you get down to a wavelength of about 1 millimeter, shown here, do you have access to the event horizon. So it's not just the scattering screen between us and these objects, but it's also the hot gas around the black hole itself that's shielding it. And we needed to see through that to understand the dynamics and have a chance of seeing this feature. So where are we? This is the basic equation that we use as astronomers. If you want to see something that's really small, the size of the thing you can look at is determined by the wavelength of light divided by the telescope size. So either we have to make our wavelengths really small so we can see something that's tiny, or we have to make our telescopes huge. Those are the only two things available to us. Now, the shadow size that I've talked to you about for both the center of the Milky Way black hole and M87 is about 50 micro arc seconds. I struggle sometimes to think about how tiny that is. If you had an atom between your two fingers and held it at arm's length, that's about 50 micro arc seconds. If you put an orange on the moon, that's about 50 micro arc seconds. If you had a quarter in New York and you were in Los Angeles, you could read the date on that quarter. That's about 50 micro arc seconds. So we needed to create a telescope that had the greatest angular resolution, the greatest resolving power that had ever been assembled on the surface of our planet. And we needed to see through the Earth's atmosphere, the interstellar gas that I told you about that scatters these things and blurs the image, and the hot gas near the black hole. So we knew we had to observe around 1 millimeter wavelength. And if you go through this equation, you realize right away you need a telescope that's 10,000 kilometers across. Easy, right? You just go to Amazon and you say, telescope, size 10,000. You order it. So we can't do what we would normally want to do in astronomy, which is to create a paraboloid. This is an example of the Parkes dish. And the way this works is plane waves coming in from the cosmos hit this perfect parabola, and everything, all the light rays get bounced to a focus where they combine geometrically, and that's where you put your camera. Okay, but of course we can't make a telescope like this that's 10,000 kilometers across. There is, however, a very interesting technique called very long baseline interferometry. I'm going to demystify what that means. Essentially, we take radio telescopes at different parts of the Earth. They all look at the black hole at the same time. At each of these sites, we have a hydrogen clock, a hydrogen maser clock, that loses only about 1 second every 10 million years. So as the radio waves come in, we time tag them all to extremely high precision. And we store them on hard drives as ones and zeros. So we essentially are freezing the light. And then we bring all those hard drives together to a central supercomputer where we compare them and combine them with the perfect delays that create a virtual telescope as large as the Earth itself. So where an optical telescope bounces light off of its surface and every light ray reaches the focus at exactly the right time, here we store the light and ensure by delays that we combine them just the right way. Okay, so this gives you data as though you had a telescope as big as the distance between these telescopes. Now, if we only had 2 telescopes, that wouldn't be enough. So we have multiple telescopes, but even that's not enough. Thankfully, the Earth rotates. It's good that the Earth rotates for a number of reasons, but thankfully for our purposes, the Earth rotates. And every single baseline pair, every single pair of telescopes that gives you one bit of information about the image changes its orientation and projected length as the Earth rotates. This sweeps out a virtual aperture or a virtual telescope screen and allows us to make this image. Okay, so every baseline pair you see is traced by a red dot, and after a whole night of observing, we have enough data to make an image. Now the last bit here, so we had a technique, we overcame these problems, we knew what wavelength we had to observe at, but was there anything there? Okay, so our small team, we had to be crazy enough to actually go out and do these experiments at first. And we did this with a new array that we built composed of a telescope in Hawaii, one in California, and one in Arizona. And you can see the length of these baselines here. We were making a telescope 4,000 kilometers across. Now, we aimed all these telescopes at this black hole at the center of our Milky Way galaxy. Now, if the black hole had had a finite size, so imagine that the black hole had a size. On this small baseline here, lambda over d, or the area on the sky that we're sensitive to, was so big we would have seen all the energy of this black hole, or coming from the black hole. But on the long baselines, lambda over d was small enough that we would have started to exclude some of the flux density. So we would have expected a smaller amount of energy on the longer baselines as opposed to the shorter baselines. And this is exactly what we saw. So here's energy on this axis, and this is the length of the baseline on the x-axis. And you can see that for short baselines between Arizona and California, we get almost all of the energy from the black hole we expect. But on the long baselines, Arizona to Hawaii, we saw a greatly reduced amount of energy. This was the smoking gun, because now we knew beyond a shadow of a doubt that there was something that was only about 3.5 Schwarzschild radii across. And the size of the shadow is theorized to be about 5 times the Schwarzschild radii. So we knew now that we could see all the way to the event horizon, and we were off and running. So this is the Event Horizon Telescope. It consists of telescopes in Spain, 2 in Chile, 1 in the South Pole, 2 in Hawaii, and 1 in Arizona, 1 in Mexico here. And this was just enough for us to make the first image. And in 2017, we mounted an observing campaign that used all of these dishes. They all pointed to the same object at the same time. We recorded data. Members of our team went to every single one of these sites, including the South Pole, including Hawaii, to make sure everything was running properly. Now, when I say that we bring data back from these places, I really mean we bring data back from these places. We store the data on hard disk drives, and there's so much data, many hundreds of terabytes of data, that we have no choice but to move it around by forklift. So this is Andrew Nadolsky at the South Pole packing up like 30 or 40 disk drives. Here they're arriving by FedEx truck at the supercomputer at MIT Haystack Observatory. We are unloading photons with forklifts. And here we're opening them up after their long journey from the bottom of the world. And here they are warming up in the ante-room of the supercomputer, because we can't put them in the supercomputer when they're very cold. We have to wait till they come up to ambient temperature. And then we were able to combine the data from the South Pole with data from all the other sites. Now, there's nothing new under the sun. We're not the first people to think about shipping data around. This is what 5 megabytes of storage looked like in 1956. So as you'll see, there's nothing new under the sun. We do change how many zeros are behind this 5. Now, when we got the data and we analyzed it and we calibrated it, it kind of knocked our socks off. Because again, here we see that same graph I was showing you before, energy versus baseline. But we saw this very curious bounce and a second bounce. Now you try to fit that in the same way that we fit the early data, and you can't do it. So right away we knew there had to be some edge to whatever we were seeing. Because if you use a filled disk, this hard edge here makes the energy, when you plot it like this, bounce. But the second null doesn't happen in the right place. So we know it can't be a filled disk. It's when you start to fit rings that everything starts to fall into place. And when you have crescents, reflecting the fact that maybe some of the gas is coming towards you with that Doppler effect and some is going away from you, that's when you get whole families of curves that fit the data. When we saw this for the first time, since we're used to looking at data like this, we knew immediately that we had something quite extraordinary. So we split up into 4 teams, because then we had to do the process of imaging. And the reason we split up into 4 teams was to prevent groupthink. So we didn't want everybody looking over everyone else's shoulder thinking, well, you see a ring, so I better see a ring. And then you start to fiddle with your data until you see a ring. So we split along roughly geographical lines. So we had a team in Europe, a team in Asia, a couple of teams in the US. And this is the best way I can explain groupthink. So labradoodles look a lot like fried chicken. And we did not want to be in a situation where we thought we were looking at fried chicken, but it was actually a labradoodle. And of course, it's even harder with chihuahuas and blueberry muffins. I think it's impossible, actually. I want to take a bite out of that guy. So thanks for not laughing. but this is very serious business. But the point is that groupthink really is a phenomenon, even in precision science. And we wanted to insulate ourselves from any indication that we were all trying madly to see the same thing. So on July 24th, 2018, we all converged at Harvard University, and all the teams unveiled their images independently. Nobody had talked to anybody else. All the data had been looked at completely separately, and every one of the teams saw this ring. Now, this wasn't a surprise to us because the signature was so clear, but it was a moment of great joy in our collaboration. And there were a lot of high fives, a lot of tears, a lot of hugging. But still, we weren't out of the woods yet because we needed to refine all of this and make sure that we had an image here that was reflecting what we thought it did. By the way, this is I call this the beer moment. This is not the champagne moment. This is just a nice beer and enjoying everyone's company. And this is what we showed the merged image. And this is a lot of the people responsible for it. And it's important to note there's an equal number of people on the phone with us also sharing in that moment, okay? So it's really a collaborative moment and effort. Now, the first thing that we tested was looking at other sources. So here we're looking at the quasar 3C279. This is one of those big, massive, black hole-powered galaxies that's so far away that we can't really see the event horizon, but we can see the jet coming from a bright core source. And this is exactly what we saw here. A core with a jet using 3 different imaging techniques. Okay, so when we thought we might see a ring, we saw a ring. And when we didn't expect to see a ring at all, we absolutely did not see a ring. So we're not looking at algorithms that find rings everywhere. The other thing we had was repeatable data over 4 days. Okay, so we have April 5, 6, 10, and 11. This shows you the coverage on that virtual telescope that we create. And the data were all independent, and we got the same kind of morphology every single day. A sharp-eyed observer will see that there is some evolution over the course of a week, and that's expected. We do expect for a black hole, the mass of M87, for there to be a little shift because of the orbits around the black hole. So how important are sites? As I like to say in very long baseline interferometry, just like real estate, it's location, location, location. So if we only had 2 sites, one in Mexico and one in the Southwest United States, all we could really tell is how big the source is. That's all we could do. When you have a third baseline, even though it's collinear all the way here in Chile, now we can start to see even finer features if they exist. It's when you get an outrigger here in Hawaii that you begin to see the beginnings of that ring. And it's only when you have the full array from Hawaii all the way to Spain that you can see the full M87 image that we published on April 10, 2019. So I want to tell you about how we measured the size of this and how we tested Einstein's theory. We did it in a number of different ways. I'm going to show you one here. We measured the ridge line of that feature, and we were able to find the radius and the width of that feature all the way around. And if you look at this, I think this is the last equation I have, for those of you taking notes. But so the angular shadow diameter that we measure here, remember we're measuring angles on the sky, would be that square root of 27 that I showed you before, times a handful of constants. We do need to know the distance to the black hole, though, because remember, if you have an angle, you need to know how far away that object is to relate the angle to a size, okay? Now, we know, though, that the distance to M87 is 16.8 megaparsecs, or about 55 million light years. And we know that from other methods. We can see stars called Cepheids in that galaxy, and we can use their pulsations to separately and completely independently see how far away that is. So we knew what the distance was, we knew what the angular shadow diameter was, and this gives us immediately the mass. Now this, if you take one thing away from this talk, you should be thinking to yourself, someone told me today that 6.5 billion masses, 6.5 billion solar masses were within the photon orbit of that mass. It's the strongest evidence that we have to date that supermassive black holes exist. There's no other evidence that's more strong or stronger than that. The stars orbiting around the Milky Way galaxy, that's incredible, incredible work. The closest point of approach of those stars is 1,000 times larger. So we have constrained all that mass to be within a volume that's 1 billion times smaller than we knew from the stars earlier. So the question is this a shadow of a black hole? The consensus is yes. I think 4 out of 5 astronomers agree that this is a shadow of a black hole. It matches the mass from dynamical measurements, because we can measure using some orbits of stars or motions of stars around the central black hole, and we get the same mass. It's circular to about 10%. We expect, given the geometry of this source, we would expect it to be circular. The asymmetry here is completely borne out by simulations that I showed you before, with one side being brighter than the other due to the rotation of gas around it. This is consistent with Einstein's theory at the 17% level. I'll talk to you a little bit later about how we can sharpen that up, but basically it's the fuzziness of this image that contributes to that 17%. So we're perfectly consistent with Einstein, and with future observations, we'll be able to make that even better. And also this allows us to study a lot of the astrophysics around black holes. This is a new window onto our study of the unknown. The other thing that's really interesting about this particular result, which we've never seen before, is that now we can tell what the orientation of the spin of the black hole is. So if you take your right hand and you point your fingers into the page and you curl it around so the gas is coming towards you from the bottom, your thumb is pointed in the direction of the black hole spin. We call this the right-hand rule in physics. So for the first time, we know that the orientation of the spin has to be into the page, and that the jet coming at us is coming from the south pole of the black hole. The one going into the page is from the north pole of the black hole. Now for Sagittarius A star, I don't have time to go into all of this in great depth, but it was much harder to image this source. M87 is so massive that it doesn't change from moment to moment. So you can add all the data from one night of observing and make one image. For Sagittarius A star, things orbit it in half an hour. It changes its appearance completely every half an hour. So you have to almost make a movie or an averaged image to capture that ring. Now, we were able to do that, and this is the image that came out just a year ago for Sagittarius A star. It's a little bit, it's not as clear as this one, but there's a distinct ring, and this ring is quite robust. Other groups have analyzed the data separately from us, and they come to the exact same conclusion. So we're definitely looking at a ring, and the size is also consistent with Einstein's theory to within 10% or so. So we've observed a 100-year prediction of Einstein's gravity. We've used the geometry of space-time and the masses of these black holes to confirm that. We have see the north-south asymmetry here. And this is, as I said, the best evidence for the existence of supermassive black holes that we know of. Now I'm going to turn for the remainder of the talk, like in the next hour, I'm going to turn to what we're going to do next. So how are we going to improve on this? And the answer is that the biggest problem we face is that we don't sample enough of the Earth-sized virtual lens. Simply put, we need to add telescopes to the array in order to get higher definition images and to hope to make movies. So what I'm showing you here in blue are all the sites that we use now in the Event Horizon Telescope, and a number of us have surveyed the whole globe. And in red are all the sites we could put a new telescope at. Now this is really interesting because the secret sauce of the Event Horizon Telescope was that we went to existing telescopes, we brought our own homegrown electronics, and we made them all work together in a way that no one of them could work by themselves. Now we have the luxury of putting new telescopes in new places, and it's been a wonderful experience to work with the whole team figuring out where are the optimal locations around the globe to do this. So this is what the EHT looks like today, and you can see here that for M87 and for Sagittarius star, we fill out this virtual lens. This is what it's going to look like when we add these points in teal here, one in Las Campanas, one in the Canary Islands, one at Haystack Observatory in Massachusetts, one in California, and one in Baja, Mexico. And you wind up getting much more of a filling factor of the Earth-sized virtual lens. And when we add even others that we hope to bring on over the coming decade, we get near complete coverage. There are no more holes in this Earth-sized virtual lens. This is what's going to allow us to make movies and the ultra-high definition images that will let us connect the black hole to that outflowing jet, which we can't see yet. So when I talk about that jet, this is what I mean. On the left, you see a computer simulation of the M87 black hole here with the jet moving off to the right. If we could image this, we'd be able to unlock the secrets of how black holes power these jets that can pierce entire galaxies. Because really, it's that feedback. It's that redistribution of matter and energy on galactic scales, which imprints on the night sky the structure that we see. With the next generation EHT, which we unimaginatively call this new project, this is the image that we can make. So we can get very high definition pictures, not only of the black hole, but also the jet. But more than that, if we observe every 3 days and do nothing more than stitch together those images, we can make movies. So this shows...
Hey, Ted, how much more do we have?
And this shows what we can reproduce just by stacking every 3 nights.
There's about another
So we're
10
extremely
minutes
excited by this because we think that by the end of this decade,
stuff.
we will realize
Then it gets
black hole
more
cinema
speculative into
for
the
first
future.
time. And for those of you who have not
All
already
right,
donated
thank you.
to the Kaufmanis lecture, we're looking for executive producers. So if you have a spare atomic clock in your attic, please get in touch with us because we know right where to place it on the Earth. Now for Sagittarius A star, it's a harder problem. Remember, Sagittarius star changes its appearance every half an hour. So we need to take instantaneous snapshots. So what you're going to see here in this inset is the Earth-sized virtual lens, but we only have aggregated all the data for 10 minutes or so. And this is the simulation you see here. This is the simulation blurred. And this is the reconstruction using a specialized technique that enforces continuity from moment to moment to smooth out the temporal variations and give us the best look that we can make with a movie. So you can see here it's spinning around. With the blurred image, you can see that spinning also. And with the current techniques, we can begin to see this rotation of the matter around Sagittarius A star. And this is important because up until now, we've tested Einstein's theory with the bending of light around the black hole. But if we could measure the orbital periods of matter around the black hole, that would be a completely different test of Einstein, for the simple reason that matter can never travel as fast as light. It has to travel different paths around the black hole. So we think that this is also entirely reasonable. And the wonderful thing is that the algorithms we use to process these data are getting better all the time. So this is just the beginning of what we think we'll be able to do. So in short, here's the model, and here's what we think the next generation EHT will be able to do. Give us the first look at the dynamics around the black hole. But of course, we're never quite satisfied, are we? And we asked ourselves, what would happen if we had satellites in orbit around the Earth? So on the top here, you see the Earth rotating, and we're building up a little bit of that Earth-sized virtual lens. And if you had 4 orbiting satellites in low Earth orbit around the Earth, this is what you'd wind up seeing in under an hour, a near filled aperture. And this would unlock all the dynamical properties close to the event horizon for one of these black holes. And then we started thinking, well, what if we put a telescope very far from the Earth? So much farther than the moon. This is at the second Lagrange point. This is the area where the James Webb telescope is. It's about 1.5 million kilometers from our planet. And if we made a telescope that big, if we made a virtual telescope 1.5 million kilometers across, every black hole in the universe would come within range, and we could have the possibility of imaging it. So there'd be no black hole that we know of that was supermassive that we couldn't image. So this is kind of a dream, and there's already a project called the Event Horizon Explorer that is aimed more towards the left side here at a geosynchronous orbit that we think hopefully will launch within the next decade or so also. So the next generation telescope will make wide-angle movies showing us the jet and the black hole, and the Event Horizon Explorer could zoom in and show us the details of these rings of emission around the black hole itself. So we have a model, we have the next generation EHT, and a space improved Event Horizon Telescope could show us something like this, a remarkable progression only over about 20 years. So we truly live in great times when we think about black hole science.
So first, there's an IQ test here. I have 3 pictures that are sort of related. Which one of them is the before, the after, and the truly before? Here's the first, not necessarily in sequence. Here's the second, and here's the third.